Okay, and you can go back to screen view, and we're in good shape. Okay.
So you're actually separate from them and
Okay, that's great. Thank you. Okay. Welcome, everyone. Oh, thank you. And thank you also, folks who are on the phone for the webinar. You should be able to access this on the screen. So are the folks on the phone seeing the presentation right now? Someone say yes.
Yes.
Thank you. That's good. My name is Sean O'Leary. I'm the pretty new communication director with the Northwest Energy Coalition. And before Ken gets started with his portion of the program, which is 99.9% of it, there were just a few things I wanted to mention to everyone here. We have, in the coming weeks, a couple of major events coming up, starting with Ken's presentation today. In 3 weeks, on the 24th, in Olympia, we're going to be doing a day-long workshop on the subject of whole building energy and pay-for-performance programs. So if any of you has any interest in that field, it would be a fascinating place to be, because we're going to have, at this point, I think 6 presentations, including from folks up at Seattle City Light and from the Energy Trust here about pay-for-performance programs in both of those cities. And we'll also have a series of experts who are going to be coming in talking about the underlying technology and some of the quantitative challenges associated with that. Yeah?
I'm looking forward to that workshop, and I asked Kat whether residential was going to be part of that at all, and she wasn't sure.
Yes, it will be. We haven't. No, we probably ought to.
Oh, okay.
Oh. No, you can take the chair. Okay. Excuse me. Jake Oster from Energy Savvy is specifically going to be talking about residential. His will be one of there were 6 full presentations that day, and his will be one of those. So, yeah, if there are any questions that you have, if there are any questions that you have about the pay-for-performance workshop, just let me know. We're going to be releasing probably tomorrow the full agenda, and you'll see the speakers. And I think all of you are on the mailing list, so you'll see that coming through. And of course, the other major event that we have upcoming in the next few weeks is that on November 17th, we have the Fall Conference, which again is a day-long series of primarily panels in which we'll have people discussing a variety of issues relating to clean energy and its integration into the grid, and quite a lot of other topics aside. So I hope you'll put that on your calendar too. And then, of course, that night we have our annual gala where we'll be doing an awards ceremony, and we'll have meetings the next day of various caucuses. So you all are invited, and so I hope you can do that. And so without further ado, I think everyone who's dialing into the webinar, I know you can see Ken's screen. This is Sean O'Leary. I'm the Communications Director at the Northwest Energy Coalition, and we're about to get started. So thank you. And so without further ado, here is Ken Dragoon.
Hi. Thank you. Okay. Okay. So, thank you all for coming, and I'm impressed with the turnout. It can't be me, so I think that means that the topic is of interest to a lot of people, and that's a great thing. I'm glad for that. I started my career a long time, over 3 decades ago, at Bonneville Power, and I like to tell people I started in my career figuring out how to a variable energy resource that it wasn't completely predictable with a 40% capacity factor, and that is the Northwest hydropower system. And it was actually a great background for what has evolved since then with all the wind and now solar. Very exciting. I worked for PacifiCorp, and that's where I really got started with wind integration work. Seattle City Light approached us with their share of the State Line Wind Project. It was in PacifiCorp's service territory. Asked PacifiCorp to take the power in and send it back on fixed and known schedules. And that hit my desk, and I was asked to evaluate what that would cost, what it would cost to provide that service. So that was my first wind integration cost study. And it's there. I worked for the Power Council for a couple of years, focusing there a bit on the issue of oversupply. Not crazy about that term, but it was better than overgeneration. And that'll creep into the presentation today. I worked for Ecofis for 2 years, which is a sustainable energy consulting company out of the Netherlands. They had an Oregon office. They left, and I became a consultant. Flink Energy Consulting since then. In 2010, while I was still at Renewable Northwest, I wrote a book on how the analytical aspects of calculating wind integration costs. So that's sort of been my area. And I had a master's in physics a long time ago. Let's see. So I'm skipping around the slides a little bit, but this was the agenda I had in mind for today. I don't think any of you have seen it. I tried to model it after the title, which I was given sort of late in the process. I've actually given this talk a very similar version of it before to Renewable Northwest, which is how I got the invitation to come speak. So it's largely that presentation. It's a little bit more focused, I think, given the title that was advertised, a little bit more focused on the integration aspects, getting to power systems that rely primarily on renewable energy. Originally, it was more about power system fundamentals for advocates trying to deal with utility electrical engineers and bumping up against terms like VARS and inertia and dynamic stability, and not being comfortable enough with those terms to be able to stand up to that and speak intelligently to it. So that was kind of the plan. So that's my plan, but I would like to hear, something has brought you here today, and so if there are specific issues people would like to hear emphasized or covered, not gnawing at you, now would be a good time to throw them out. So I'd rather tailor this to what your needs are than to what my imagined needs are.
Jeff Bissonette with the Solar Energy Industries Association, state trade association for the solar industry, and we're increasingly interested in sort of integration, transmission, in siting solar, both large scale and rooftop, and so it seems like those very broad issues kind of are impacted by sort of the integration things, but those are some of our specific things that our members are wondering about these days.
Okay. Yeah.
Perhaps we can just go around the room and introduce ourselves, and then people can say if they have something at that time. Would that be okay?
Yes, if we can be really quick, because we'll be cramped for time.
Be nice.
You want to start?
Sure. I'm Michael Getz. I'm a staff attorney with the Citizens Utility Board of Oregon.
Fred Hewitt, Northwest Energy Coalition staff here in Portland.
Jacob Goodspeed. I'm a pricing analyst for PGE.
Dick Wendershed, Bonneville Environmental Foundation.
Michael Furz, running the Energy Division of the Washington State Department of Commerce.
Wendy Gerlitz, Northwest Energy Coalition.
Zach Waterman, Sarah Club.
Chris Robertson.
Greg Tom McCochum, Home Performance Guild of Oregon.
Liz Jones with Power.
Jerry Bauer, Northwest Natural.
Wayne Moore, Director of Power Management at Seattle Citywide.
Jefferson Adocia.
Julie Chapman, League of Women Voters.
Evan Ramsey, Bonneville Environmental Foundation.
Steve Antop, Solutions, and PGE and their proposal.
Jeff Hammerlin, Portland State University, and faith-based groups, and members of the Northwest Energy Coalition.
And I'm Sean O'Leary with the Northwest Energy Coalition. And would the folks on the phone like to introduce themselves?
Ricky Seglin with Renewable Northwest.
Chuck Johnson, Oregon and Washington Physicians for Social Responsibility.
Kate Von Rees-Barron, PGE.
I'm sorry, who was that?
Kate Von Rees-Barron, PGE.
Oh, thank you, Kate.
Huh?
Tony Slayton-Barker.
Pat Smith, Northwest Fire Council, Montana.
Tony Slayton-Barker, Kaufman Engineers.
Diego Rivas, Northwest Energy Coalition.
And it's J.J. McCoy, Coalition staff.
David Posner, Climate Policy Initiative.
Okay. In the back of the room.
OPUC.
Jenny Hall, Energy Trust, Solar Purpose. Lynn Merritt, Let's Talk Climate.
Okay. Well, nobody brought up any burning issues, so I don't want to assume.
Got one. There's often talk about the ancillary benefits of distributed generation and solar in particular, and I don't fully understand how that's quantified or what those support services could be.
Okay.
And wasn't clear, but I brought up the PG IRP and the I'm just trying to better understand.
Okay.
So, and I'll just I think you're going to cover this, but the role that renewables can play in grid reliability.
Okay.
Ken, may I intercede? People on the phone who are doing this by way of webinar, if you look at the top of your webinar screen, you'll see that there's a little messaging bubble up there. If you have questions that you would like to submit, because it's sometimes hard to hear it over the phone from here, you can use the messaging bubble, and we will see it at this end, and we'll address whatever issue you have as well.
Okay, very good. And if you would mute your phones in the interim, that would be good.
I just want to ask, are the slides going to be available following the presentation?
Yes, I believe.
Yes. In fact, the webinar is being recorded, so the entire session will be available on the site.
Okay. Well, we should probably get started. First off, how many engineers and science background people are there in the room? Okay, so you can keep me straight, but you may fall asleep in the meantime. Okay, so I want to start out with power system fundamentals. That's kind of my physics background coming through. I remember my first week at Bonneville, one of the managers got up and made some big point and emphasized it by saying, and it doesn't matter which way the volts are flowing, which doesn't actually make any sense. So I feel this need to go through some of the fundamentals, and I think that'll help understand what comes later, which is about how we integrate, how you operate a grid primarily or entirely off of variable resources like wind and solar. So this is slide 4. And I kind of mentioned all of this. I think I was originally approached by Renewable Northwest. Their advocates often didn't have a very strong engineering background, and engineers were throwing out terms like VARs and volts, amps, watts, synchronous condensers, dynamic stability inverters, all of which are potentially issues that come up in this integrating large amounts of renewables, and they weren't really comfortable speaking to them. So the a big part of the foundation here is that. And then at the end, we're going to come back around to this roadmap of things that we have figured out based on a paper that I wrote when I was at EcoFIS. This roadmap, basically a menu of things that you need to do in order to transition a power system from the kind of systems we have today to power systems that rely primarily or entirely on variable renewable energy. And this is one of my favorite ever quotes. There are few things as toxic as a bad metaphor. I think we have lots of bad metaphors in the electric power industry. We also have, forgive me folks from the utility side, but there are a number of bad ones, and I've fallen prey to a bunch of them. One that we're going to hit hard today is operators have to match supply and demand at every moment, or the system will black out. And I've been in BPA rate hearings where that's come up, where BPA set an amount of reserves, and then people in the audience were like, well, what happens when that runs out? Because it's only at the 99.97% percentile level. What happens at that 0.03%? Does that mean the system blacks out? And it's because of this metaphor people believe that. And so we're going to talk about why that's not true. Firm capacity was an interesting thing that's come up, which I think is problematic. And backing up wind is another one of my pet peeves. Again, I know there are people probably in this room who disagree with that, but the whole idea of backing up wind, I think, is sort of wrong way around. This quote is from Mary Catherine Bateson, and at first I only heard the first part. There are few things as toxic as a bad metaphor, but it goes on. The end of that sentence, or the end of the quote is, you can't think without metaphors. So we're actually going to have some metaphors, I think some pretty powerful in this presentation. And I think it's important for us all to recognize that we have assumptions about how the world works, build up these models in our head, and read them in order to simplify our world. And we just have to now and then question them and make sure that they make sense. So here's a metaphor for those of you who aren't already electrical engineers. The metaphor that if I don't leave you with anything else today, it's this. And again, this is back to my background in physics. Electricity flowing through wires is like water flowing through pipes. And so that's a metaphor that works and explains about 90% of how electricity acts. The 10% that's left out is really interesting, but when we're dithering about how does electricity work, why is this happening, 90% of the time you can figure it out just by thinking of electricity as water. Electric generators are analogous to water pumps in this analogy, and power is defined in the electrical system as voltage times current. You know, what's voltage? What's current? Well, if you think of voltage as water pressure in this system of pipes where we're pushing water around, that's completely analogous. And the current is how much water, and the power is product of the two. And that's literally true with water as well. Water power is the amount of pressure coming out of the pipe times how much water is coming out of the pipe. Okay. We're going to hit this again, but you're forewarned. First, we're going to talk about energy, work, and power, because there are so many folks who get kind of tripped up about the differences between energy and power, and I'm hoping to give people a more basic sense of what these things are. Bear with me a little bit. This shouldn't take very long. So it started with the notion of work. It was an 18th century concept of real work, not what we do today at our computers so much, but things like drawing water from wells and grinding grain. And the definition of work was really a force, which is how hard a thing pushes or pulls, and it's commonly in the U.S. measured in pounds, times the distance, how far you have to pull that thing up, or the distance around for the grinding wheels. And, you know, that's a thing that steam engines can do, and that was a huge improvement when we didn't have to have people and horses doing this work. We had engines that could take place of the animals that were actually stronger and more durable. So the unit of force is the pound. The metric unit is the Newton. How many people knew that? The engineers. The Newton. So I am representing the Newton here with an apple. This is not a Newton apple because I couldn't find one. They're green, I think. A Newton is about 1/4 of a pound. This is actually, I weighed it. It's about 1/2 a pound, so it's too big. But okay, there's a Newton, and the reason that I'm bringing this to your attention is because the unit of work is force, the Newton, times distance in the metric system is a meter. So a meter is about 3 feet. So if we'll pretend that this is actually a 1/4 pound or 1 Newton apple, if I lifted it from the floor up to the tabletop, that's about 1 Newton times 1 meter, so a Newton meter, and that's in the metric system, that's called a joule. How many people have heard of a joule? Oh, more. Okay. Well, that's surprising. Okay, so a joule. So nobody thinks about the Newton. Even in Europe, they talk about kilograms, not newtons. But so it's long forgotten. But it gets around to the joule, and the joule you may not have heard of, but it's going to make a more common appearance here in a moment on the next slide. I'm on slide 9 for energy. So energy was defined as the ability to do work. So any system, any substance that had the ability to exert a force over a distance was said to have energy, and you could measure it in joules. A joule, of course, is not a huge amount of energy. And as I demonstrated, lifting the apple from the floor to the desk is not a Herculean effort. So if we do have other units of energy that are bigger, and a very common one is a kilowatt hour. And a kilowatt hour is 3.6 million joules. So that's one that we're familiar with. I'm just trying to tie these concepts of energy and work to things that you're more familiar with. So energy comes in many forms. Heat, if you heat something up, it expands. The expansion can push on something. Chemical energy, explosions, electrical energy can be converted into mechanical energy with motors. Kinetic energy, I can throw I have a little picture here on the PowerPoint of a light switch. I tried to think of something you'd have to push through a distance. So I happen to have a push button switch. So anything that could push that button has energy. I could throw the apple at it. So the apple in midair has energy because it could hit that switch and perform. So energy is, think of it as a kind of an amount of stuff. If I lift the apple to the table, I've done that once, I can actually get that energy back out of the system by rolling the apple off the table onto the floor, and when it strikes the floor, it could push this button or something like that. So they can move back and forth. But it is a quantity of stuff. It's not a physical stuff, but it's an amount, okay? Stressing that because of power. The two get mixed up. Power is really the rate at which energy is generated, consumed, or transferred. So this is how fast energy is being done. I can lift the apple to the table in 1 second. That would be 1 joule in 1 second. I can do this is actually 2 Newton apple, so if I do that in 1 second, that's really 2 joules per second. And the unit of power is the watt. So here we've gotten newtons, nobody remembers, Newton meters, nobody uses, to joules that a few people of you know. Joule per second is a watt, so it's a rate at which energy is being performed or transferred. So again, using it like a car analogy, the energy in the car is represented by the fuel in the tank. The power of the car is like how fast it could climb a hill, or how quickly it drains that fuel out of the gas tank. In a hydro reservoir, the energy is represented by the water in the reservoir. The power is the rate at which it's coming out at any particular moment. All right. Any questions on that? Got it. Okay, so now electricity, and we already sort of covered this, so just a little bit of review. Voltage is the pressure, well, electricity is the flow of electrons through a conductor being usually a wire. Sometimes it's the air with lightning, and sometimes it's you if you get shocked, but usually, we like to keep it in a conductor and it gets transferred safely. But it's the little electrons going through a conductor, and you can't see an electron, so this is, kind of a little esoteric, but that's what's going on in there. And the electrons move because of this thing the physicists like to call electromotive force. More commonly, we call it voltage. It's some force that's pushing. It's really a pressure pushing those electrons along the wire. So volts is like pressure. And the amount of electrons that move is the flow, which we, in electricity terms, you call current, and it's measured in amps. So we have volts and amps. And power, again, is the product of the two. It's volts times amps. And volts times amps equals watts. So that's how you get from two things that are sort of nebulous to something that we're at least more used to hearing about. Okay. The one other thing to know is that, and this makes a cameo but important appearance, the losses in a power line, so when those electrons are moving through the wire, there's actual friction. It heats up the wire. And that heat takes some of the electrical power away from, you're trying to deliver it at the other end of the wire. So those are heat losses. They're called joule losses, or resistive losses, or I squared R losses. So I is usually the letter, that algebraic symbol that's used to represent current. So you take the current in the wire and you square it, and you multiply by the resistance in the wire, and you get the amount of heat that's being generated off that wire. Okay. Not a big deal, but we talk about transmission and distribution system losses, and that comes into play there. But also, it explains why there are high voltage lines.
Sure, but what causes resistance? It's the ability for that wire to heat up and how much it can heat up, or?
Good question. If I were to try to explain it, I think that it's kind of like the stickiness of the electrons to the wire itself. So as it moves along, it's sort of rubbing against the rest of the material in the wire that sort of starts shaking back and forth, and that's what heat is.
And just over time, have we improved reduced the amount of resistance in those wires?
Well, yeah. I mean, it's basically a property of the material. It's somewhat a property of the geometry. So there are things that are done. I mean, the big breakthrough is superconducting wires that have no resistance. But that's a different lecture.
Maybe it would help to explain why DC wires are have less line losses than AC?
So on slide 13,
Okay, sorry.
we define DC. So direct current is sort of familiar. It's what comes out of batteries, and it's the most directly analogous to the water flowing in pipes scenario there. So a basic circuit means it's a loop. It's got to be a closed loop. The water has to come from somewhere, and it ends up going in a circle. We don't always do that with water, but with electricity we normally do. So we have in this slide 13, you have a battery, which is analogous to the pump. You have a switch, which is analogous to a valve, faucet. The wire, of course, are pipes, and then you have a light bulb or something, some kind of load. It could be a motor. It could be a water wheel in the case of water. So completely analogous. The electricity comes out of one side of the battery, goes through the wire, and goes back into the other side. So we're not creating the water or electricity, we're just moving it around. Slide 14, making electricity the usual way. I used to say that 99.999% of electricity was all made in the same basic way. That's changing. But let's go back 150 or 60 years to see a demonstration. The engineers will all yawn at this. This is for you on the phone. What I have is a coil of wire. I just bought this from Radio Shack the other day. So a coil of wire is just one long piece of wire wrapped around and around and around a cylinder. And I think Michael Faraday noticed that when you put electricity through wires, it makes a magnetic field. It acts like a magnet. It has the properties of a magnet. And the last time I gave this lecture, nobody in the room knew that. So I brought a demonstration. So here is a car compass. And I have this little 6-volt battery from Radio Shack. I don't mean to advertise for them, but there it is. And I'm just going to put the coil near the compass. And you'll see if I connect the wire, the compass moves. Now, Michael Faraday discovered that 150 or 60 years ago. And so that's pretty nifty. Who knew? I'm not going to explain it. I'm not sure there's a great way to explain it, but that's one of the facts of life. Well, there's an interesting corollary to that. I am moving electricity through the wire to make a magnetic field. It turns out if I move a magnetic field around the wire, or vice versa, if they move relative to one another, it makes electricity. Now this is a more subtle effect, so I have a meter to show that. So let me connect my meter up. All right. Now I need witnesses.
Generator.
That's zero, right? All right, here's a magnet. I guess I got to prove that. Wants to pick up this paper clip. We can't get rid of it. Okay, so this is a magnet. If I move these relative to one another, we will create a little electricity, which is being picked up by the meter, right? All right.
Numbers on there?
What numbers on there? What kind of numbers? About what kind of numbers?
0.006, round to like 100th of a decimal.
Yeah. If you put iron, you know that magnets and iron sort of attract one another. I can actually concentrate the effect by putting some iron in here. We should be getting some bigger numbers.
Like 0.03?
Yeah.
0.02?
So like 10 times bigger just by putting some iron in there. So it turns out that's how we make electricity. 99 point, I don't know how many decimals now. It's not as many as it was. Because why? Solar is the only real way of producing electricity that's around that. And what?
Photovoltaic.
Yeah, photovoltaic. So you have wind turbines, these big blades, they're just spinning magnets past wires. You have a combustion turbine, it's a jet engine, which is a bunch of fan blades arranged around an exploding fuel source and air. It spins those blades, or a shaft that goes and spins the magnets around wires in the generator. And nuclear power, all it does is heat water, boil it, goes through a steam turbine, spins blades, turns magnets past wires. Okay? Here's another sort of picture of that. Yeah, it has some other byproducts. So this is just, I'm on slide 15 for you on the phone. This is just a picture of kind of the insides of a generator. And here is on slide 16, I'm getting a little bit closer and closer to showing you what a power generator looks like. I don't know if I get all the way there, but this is a bit closer, where the magnetic field is not actually, is often, not always, but often not produced by a magnet, but it's produced by another coil of wire. So it takes electricity to make electricity, which is the whole black start thing, because a lot of generators can't start unless they have a power source to energize the electromagnets to make the field that then rotates. Interestingly, the energy is not coming from the field, it's coming from the motion, the relative motion of the field with the, so you can have a superconducting electromagnet that doesn't actually consume any power to make the magnetic field. And so slide 17 here. Balancing supply and demand, I sort of stole this picture. So now we're getting electricity and energy and power. They're all sort of coming together in this. And I said this notion that the operators are every moment keeping the supply and demand equal. You know, I believed that myself for most of my career until it dawned on me, wait a minute, I'm a physics major. Energy is never gained or lost. It just transfers from one form to another. You can't generate power and have it not go anywhere. It goes somewhere. And so supply and demand are, well, not demand, but the generation and load are always equal, just sort of by definition. It's not some engineer in the back room making that happen. Now, if supply and demand are out of whack, there are things that go on, and I've got a demonstration. We're going to show what that looks like. But I stole this picture. I've been thinking about it, but I actually saw this picture on slide 17, which I thought was really good. So at the top here where it says producers, these are generators creating electric power, putting them into the grid, which is sort of this series of reservoirs. They're very shallow reservoirs. And then there are taps where people are taking energy out of the system. And because these are shallow, you kind of do have to keep them in balance or else bad things can happen. And the level in these various tubs, shallow tubs, is proportional to the frequency. So one of the things that you see, I guess I didn't go through that yet. We'll talk about frequency here a little bit more. Maybe I should back up. We'll talk about frequency again in a minute. But, well, maybe now is a good time. So let's go back one. So this is alternating current, which I didn't talk about enough. So in alternating current, basically what you have is the electrons flowing one way for a bit, turning around and going back the other way. So you don't have, unlike, sort of the water analogy where the water is all flowing one way, it still works, the analogy still works, but the water is more or less vibrating back and forth. That's what's going on in AC. And that happens because of the way we were making it with the magnet. The magnet comes forward towards the coil of wire. It's producing electricity in one direction, and when it goes away, it's producing it in the other direction. And this wire is another, it goes around and starts facing the other pole. So you get alternating current. Electricity flowing one way and then flowing back. And there are a number of characteristics which we're going to come to in just another moment, but I want to do another demonstration. Okay, this on slide 18 is a picture of a generator. It's actually the picture of a disassembled generator. It's a picture of this generator that I have mounted to a board here. Okay, so it's on an axis. There are a bunch of magnets. Those discs in the picture are magnets on the left-hand side, and then coils of wire on the right-hand side. And this, when you turn the magnets past the coil of wire, it makes electricity. So I have a little power grid set up here.
And this is all really cool.
Microgrid. I was waiting for the but.
Totally cool.
All right, I have a little grid here. Here's the wires coming on. This is actually a DC generator. I just discovered that.
What is that generator used for?
What
part of it?
What is it used for? I think, at the moment, it's just being a demonstration. This is, I found this the other day. I was so excited that I found it. They actually, the company that sold it had a video online where it was connected to some squirrel cages, and they blew air past it. It generated power. Yeah.
Well, of course, it's worth mentioning that any electric motor ran in reverse can turn into a generator.
Yeah, we're going to see that sort of in a moment, too. All right, so I have a little grid. I have a little light bulb here that it's maybe too far for some of you to see, but there's a little light bulb here. And I have everything I need except the prime mover. The prime mover is the thing that spins the generator. And I didn't bring one of those. I need a volunteer. I need a sentient prime mover, okay? You're going to have an actual part in this. Okay. You had breakfast, right? So you're going to be able to do this.
Yeah.
All right. I want you to turn this. You don't have to turn it fast. I just want you to turn it at a constant rate of speed. Okay? Go ahead and do that. All right. There's nothing connected to this generator, so we're already demonstrating supply exceeding demand. There's no demand on this. The generator has not yet melted down. So it is possible. Now, it's not generating any power because there's no load on it. All right, so I'm going to connect it to the load, and we'll see what happens. All right. So I want to know what you experienced when that connection was made.
A lot of resistance. As you can see, I'm starting to push it that way.
All right. So he actually felt it, and that's what happens in real life. When you increase the demand, the prime mover has to work harder. And what happens if you don't work hard enough? Back off a little bit. All right, it goes dim. We've got a brownout. All right, light that bulb again. Pretty good. Oh, what happened there? I connected a second bulb, and it got even harder. So it got harder, and the first thing he does when that happens is he slows down. So now thank you. So in AC power, one of the important characteristics is how fast that rotor is spinning. It creates this beat. It's the rhythm of those electrons going back and forth. And in America, North America, we use 60 cycles per second. So the electrons are going back and forth 60 cycles a second. Doesn't have to do that. It's just the standard. In most of the rest of the world, they use 50. And in some parts, like the German trains, electric trains use like 13. So it's a choice. But that's what's going on. And as we saw, if you add load to the system and you're not prepared for it, like if I told you ahead of time, okay, I'm going to do this, you might have gotten ready to spin harder. But if you don't know, and I connect that thing, the first thing that happens is you're spinning that more slowly. So that 60 cycles per second drops. And the opposite happens too. If I take the load away and I don't tell him, he's going to start spinning faster because now it's easier to spin, right? You felt it's physically harder to spin this when there's a load on it. Okay, does that make sense? So that's kind of an important thing. So there's another thing that happens. We have, when we generate AC power, you have voltage and you have current. And I said the electrons are going back and forth. Well, the pressure on them, the voltage is going back and forth, as well as the actual motion of the electrons. And in the ideal system, the pressure and the current are in phase. They're both doing the same thing at the same time. That doesn't have to be. And another issue you have with AC voltage, like this is, I think, a 6-volt battery. Yeah, 6-volt battery. What's the average voltage on an AC system? It's always 0. Half the time it's plus and half the time it's minus. So the average is 0. So when I plug in something to the wall outlet and I say it's 120 volts and it's AC, all of our power is AC, what is that? Well, some of you, what they do is they do a mathematical operation on it where you take the voltage at any moment and you square it. Now it's always positive, and you average the square of the voltage and then take the square root of that. And that's called root mean squared voltage. So when we talk about 120 volts or 200 kV or whatever it is, it's actually RMS. Now, so the reason I bring this up is in DC, voltage times current is power, but in AC, you can't, it's voltage times current is still power, but it's instantaneous, so you have to look at every moment. So that's why we use RMS, because now RMS voltage times RMS current is average power. It's actually called apparent power. Okay, voltage times current is now, in an AC system, it's called apparent power. And it's measured in volt amps, which is sort of annoying. But what we call watts is real power, and then there's another component called reactive power, and that's where this whole idea of VARS comes in, which we're going to talk about some more in a moment. Where do I? Yes, in a moment. So first we're going to talk about inertia, because that's another big topic that's brought up in the context of renewables. Conventional generators involve physically spinning heavy metal equipment. I'm on slide 20 for the phone people. And as someone pointed out before, if in this diagram on slide 20, I have a magnet spinning past these coils of wire making electricity, and I can connect that to a similar device over here. Now, as the magnet goes by, it produces electricity. The electricity goes, and now that electricity energizes these magnets, right? If I'm moving this one, then that electricity comes over here. Now, all of a sudden, we have basically a rotating magnetic field in here. What's this magnet going to do? It's going to go follow it around. So when I spin this one spins. Which one's the generator and which one's the motor? They're basically the same device, which was your point. So let's say they're both generators because I have something spinning both of them. They are electromechanically linked together. And if I have two of these generators and they're both connected together and maybe they're connected to a load, and I try to stop one, the other one's still going, it's going to try to turn this one into a motor and keep it going. The system acts like one big system. The generators are all linked. And let me disconnect this a little bit. So here's my generator, and if I spin it, you can see it just keeps spinning. That's basically what inertia is. If it had no inertia, as soon as I took my hand off it, it would stop. The fact that it has some weight to it, some mass to it that's spinning, gives it this property we call inertia, which is basically what? It's the tendency to continue to spin. And even if I connect it to the load, okay, now it doesn't want to keep going, right? But you can still see, when I take my hand off it, it still spins a little bit. So that inertia, the kinetic energy involved with the spinning of that metal, is creating electricity even when I've taken the power away from it. And that's what we call it, that's what people are talking about with inertia. So that if there's a fault in the system or something goes haywire, there's still some kinetic energy in these spinning devices that can muddle through, maybe only for a few milliseconds, but those are important milliseconds. Okay. There are devices, I'll go through my little bullet here. Systems with lots of inertia are more stable. They'll tend to muddle through more problems on the grid. If there's a short or something or a power outage, something opens up, they'll just keep going. And systems with lesser inertia, the voltage drops, the frequency drops, bad things start happening pretty quickly. So this inertia is kind of a big deal for folks who worry about power system stability. There are things called synchronous condensers, which are what? Well, basically they're just generators, motor generators, which can be operated for a number of purposes. But one of the things that they do is they add inertia to the system. Okay? And any generator can be a synchronous condenser. So when people say, I wrote this paper, and the paper was sort of themed around, how do you operate a system without this kind of generation? Because this old way of spinning magnets past coils of wire is sort of going away in favor of another system involving inverters that I'm going to talk about in a moment, and they don't have this necessarily. They don't necessarily have this property of inverters, and of the spinning devices, which are also called synchronous generators. And I went back and forth with electrical engineers on this, with reasons that I'll explain. But they finally calmed down when I said, well, look, we could just leave the generators in place. You could leave the coal plant generator actually spinning. Basically, it's consuming a tiny amount of energy. You don't have to power it with coal or anything else. You spin it like it's a motor, and it can provide the inertia that you had in the system to begin with. And that calmed them all down. So yeah, you can do that.
Any question on that?
Uh-huh.
So when you say stability, do you mean frequency stability? Because you're less likely to slow the whole system down if there's a lot of inertia? Because I was thinking a scenario where if there's a dramatic cut in demand, you'd want to be able to quickly reduce power supply.
Yeah.
If everything has a lot of inertia, it might be hard to do that.
Yeah.
Presumably you need something.
There are two sides to that coin. That's true. So okay, let's come back to something I sort of mentioned before. So on slide 22, alternating current. So this is a picture moment by moment. So time is on the x-axis. And V here, this black line is for voltage. The voltage is going up and down in time. I guess these are seconds. And I for current, I don't know why, but we usually use I for current. And it's going up and down. And you multiply these two numbers together at every moment, and you get this power. So the power fluctuates. But because a negative number times a negative number is a positive number, the power is always positive. So now you can actually take the average of this if you want. There's average power, but this P is really the apparent power. In this case, it's all just power. Why? Because the voltage and current are varying together perfectly in sync with one another. That doesn't necessarily have to be the case. They can get out of sync. You can have pressure without current and current without pressure. That kind of looks like this. So I've separated them out here, the voltage and the current, and now they're not perfectly in sync. Does that make sense? So they're just offset some. And if you multiply them together every moment, you get this curve. And you'll see that there are times when it dips below the positive line, negative power. Any idea what that means? Yeah, wasted where?
During the transmission process.
So this is an indication that the power, instead of going from the generator to the load, is going backwards. So you have power going backwards through into the generator. It's a good way to melt down the generator, for one thing. It's not good. Plus, it reduces the useful power that's getting to the load, right? These negatives, cut that off. Now instead of the full amount of power, you're getting less. So you may have a power line that's at full voltage capability and full current capability, and the generator too is at full capability, but it's not transferring all of the energy because some of it's coming back. So this is a very inefficient thing on the system. And this is the whole idea of reactive power. So you can separate the actual positive power from the negative power. This, of course, is apparent power. They divide it into the positive part and the negative part. And the negative part is the reactive power. Yeah?
So what I've heard is that when you've got a power factor problem in, say, a house or a commercial building, it can result in wasted energy through heating of the wiring in the building?
Yeah.
Can you, and then there might be power factor correction before, between the building and the generation plant. Can you explain why that creates heating in a wire? Or maybe that's a misunderstanding.
I'm not sure. I mean, it creates heating back at the generator because the power is going back to the generator, and it heats up. I think that if somehow you're demanding a constant amount of power at the other end, which could be true, that means the current has to go up. So you could get higher losses because the current is going in. So let's say you have 100 watts of work to do and you have a motor that's going to supply 100 watts. This starts happening. It's weak, so it adjusts itself to consume more energy, and that comes in through a higher current level, and that could heat the wires, yeah.
That makes sense. And I imagine the equipment that is used to take out, to do power factor correction, and shield the generation plants from all the end uses out there might burn some energy to do that job?
Not much, no. Basically, to fix this problem, you add a little bit of storage to store some current to get it back into place where it belongs. So the current comes in, it stores it up in this device, and then it lets it back out as the current falls. And so you don't really, those are very efficient devices, and they don't store a lot of energy. It's still only for a piece of a second. Okay, you mentioned power factor. The power factor is the ratio of real power, the actual watts that are delivered, divided by the apparent power. Power factor of 1 means there are no VARs going on. So that's a good thing. And you can have loads that screw up the power factor, and that's not a good thing. The VAR problem can be local, and it's something that can be locally corrected, as I said, with capacitors. There are things called static VAR controllers, dynamic VAR compensators, synchronous condensers, what I talked about before, and they can also be adjusted with generator exciter currents. So the thing really to know about VARs is they can be problematic, but there are technological solutions to them. And they cost something, but it doesn't cost a lot of energy, and it doesn't really cost a lot of money. So here's sort of the water analogy. On slide 25, you've got a fireman with a hose trying to put out a fire up a few floors, so you need pressure and flow. If you don't have enough voltage, you don't have enough pressure, you can't get up to the floor. You might have plenty of water, but you can't get there. You might conversely have plenty of pressure and you can get the stream up there, but there's just not enough current to do the job. Lots of voltage, but not enough current. And then there's high VARs where you get plenty of pressure, but not at the moment when you have lots of current. So you get this problem as you can do some of the work, but not very much when you have high VARs. Okay? So questions on that? All right. So inverters. Inverters are electronic circuits, basically. They have capacitors in them. I use the word capacitor. Capacitor is basically a device with 2 metal plates in close proximity, and you can connect it to a voltage, a DC voltage, and those plates will charge up with electricity. Basically, it acts like a battery, a very small amount of storage battery. Those are devices that are important components in these inverters. The basic job of an inverter is to convert DC power to AC power. They effectively make kind of a digital approximation of AC power, and sometimes it's a good approximation and sometimes not. So there are good inverters and bad ones, and bad inverters can cause problems. You don't want those. Because nothing is spinning, I should back up. So our power grid is based on AC power. So if you have a solar photovoltaic power plant, it's producing what? DC energy. In order to get that on the grid, you have to convert it to AC. And in order to convert it to AC, you need one of these inverters. But there's nothing spinning, there's nothing physically spinning in an inverter, so inherently it has no inertia. Electrically, it doesn't look like it has any inertia. So, if things go bad, the sun goes away, they just stop immediately. Inertia, but because they are digital devices, they actually have the capability of doing virtually anything. They can mimic inertia. They can provide other ancillary services like VAR control. That can be programmed into them. Some of those services cost power. So, for example, to effectively provide inertia, you just don't generate all the available power. You turn down the inverter. So let's say the solar project can produce, I don't know, 10 kilowatts at a particular moment. But instead of the inverter letting all 10 kilowatts go by, it only lets, say, 9.9 kilowatts go by. And then if it senses some problem on the grid, it can blast through that last little bit that looks like inertia. They can be programmed to do VAR control. All photovoltaics use inverters, but the other thing is most wind turbines do as well. I don't know how many of you remember in the 80s, Bonneville had these big wind turbines up near Goldendale, right? Yep. And they kept breaking down. And what would break down on them was as I understood it, was the shaft between the turbine blades and the generator. So a big gust of wind would come up, and the turbine blades would want to spin faster. But they were synchronous devices, meaning they were in lockstep with every other generator in the power grid. So that wind and those turbine blades were really trying to spin up the entire grid. And that's not happening. So instead, the crankshaft broke routinely. So one of the ways they've gotten around that is now the wind turbines are designed so that they can spin up. They produce AC power because AC generators are very efficient. And they rotate faster than the grid does. And they do that, they take that AC power, convert it to DC, and then take the DC, convert it back to AC with the inverters. So that now the wind is actually being fed into the system through an inverter. And although those inverters can be programmed to do virtually anything, there are standards by which they operate, and if you don't have the right standards in, there can be problems. So for example, in my colleagues, when I was at Ecofest, did a big report on 50-point-something hertz problem, because all of the solar inverters were programmed to cut out if the system frequency went above a certain level. So they were concerned that if the frequency did happen to jump over that level, every solar rooftop, utility grid, every solar plant in Germany would turn off at the same time, which would cause a catastrophic, reduction in power. And I talked to an operator in Hawaii. They had the same problem on the other way, which is really worse. The inverters are programmed to protect themselves in the grid by coming offline if the frequency drops below a certain level. So the frequency, they had an outage of a major power plant, and the frequency dropped just as we saw, slow down when you spin this thing, when they lost a generator, because all the other generators were trying to meet the load without it. And so the frequency dropped, and then all the solar on the island dropped out at the same time, and because that dropped, that just made the situation worse. They almost lost everything and went to a blackout. So they're very concerned about that.
Ken?
Yeah.
A question came in from one of the phone folks, and I think you may have just answered it, asking how would you describe spinning reserves in physical terms?
Oh, great question. So utilities know that power plants go out all the time. I think at PacifiCorp we averaged a power plant going out, some unit on a power plant anyway, going out almost every day. Something failed, right? So the utilities know this. So they don't have just one guy spinning this thing, because they know that what can happen is a power plant can go out and it gets harder and frequency drops, the voltage can drop, you risk a blackout. So they have to have some power plants all fired up and ready to go in case that happens. And generically, the extra power plants that are hanging around not being used or not being fully used, holding back some, maybe they're operating but not at full output. There's mandates for the utilities to hold a certain amount of generation in reserve. in case that scenario should happen. And some fraction, I think it's half of the reserves that are held for that purpose, which I call contingency reserves. Sometimes they're called operating reserves, depending. But half of the contingency reserves have to be what they call spinning reserves, which basically they have to come on at full tilt within 10 minutes. The spinning part is an homage to power plants that would be physically spinning but not under load. So you're connected to the grid, you're connected to your prime mover, you don't have to spin up the speed and then match the phase. You don't have to go through the whole process of getting a generator online. You're basically ready to go, and they're typically available much faster than 10 minutes, but that's what spinning reserve is. So they say half of the reserves have to be spinning reserves, which are available almost immediately, and the other half can come on, I think, within 30 minutes. Somebody correct me.
And what percentage has to be spinning with?
Well, those are standards set by different reliability councils, and it's changed over time. I think the most recent one I remember is 3% of your load plus 3% of your generation, but then there's distinction how much of it is, if your system is largely hydro, then you have fewer reserve requirements. Anyway, it's a little complicated, but they have standards that they have to meet. And they have these reserve sharing pools so that utilities can kind of get together and share their reserves instead of each one having to hold their own. Yeah.
If we're done with that tangent, I'm wondering if I could take us back to the using the inverters inside a wind generator to manage frequency and manage the fact that, as you demonstrated with your two synchronous generators needing to spin and together. Could some of that function be of those inverters be provided by like a load, for example, a battery that is right there with the?
Well, batteries have inverters too. So to the extent that inverters can provide, by the same token, they can provide inertia for wind projects, they can do it for batteries too.
Right.
Yeah, batteries can do that. The knock on all that, so I was arguing with these electrical engineers, you could run a whole system off of generators that have inverters, and what they were saying was, well, there are all these problems because they have to communicate and coordinate with one another in such a way that they don't make the system worse. So you could see one inverter trying to increase its output at the same time another one is decreasing, or they can go at cross purposes if they're not coordinated. And although we have examples of that working on smaller systems, they're concerned about how that would work on a really, really big system. So that was the conversation I had where, okay, we can conceive that the inverters can do all this. It makes a lot of system engineers very nervous, but if you throw in, okay, as a backstop, you can have synchronous generators. You don't have to take the generators out when you shut down the coal plant or whatever. That made them much happier.
Sorry, so in the example you were talking about Goldendale, you were saying, these shafts are breaking because they were synchronous generators. I sort of, my brain sort of followed along and assumed that ultimately all of them were switched to have inverters.
Yeah, they basically all have inverters now, but that was in 1980 something.
Okay, but do all wind turbines now have inverters?
Oh, that's probably too far to go. I'd say all modern ones do.
Okay.
But there are probably some legacy ones out there that don't.
Thanks.
Why did they switch back and forth? AC to DC, back to AC?
So you have to end up with AC at 60 cycles in order to send the power on the grid. they start out with AC because AC generators are very efficient. In order to allow the blades to have different speeds, they have to disconnect, because when the wind comes up and the blades spin faster, the frequency goes up of the AC they're producing. So they instead of guaranteeing 60 hertz off of, or 60 cycles a second off of the wind generator itself, they guarantee it off of the inverter. Does that make sense? So the AC generator that the turbine blades are connected to actually doesn't necessarily have to produce 60 cycles power. It can vary over whatever range they want.
You're smoothing it out there.
Yeah, you can't connect that directly to the grid. So they turn it into DC, which is frequency neutral, and then they go back to AC frequency. Okay. So AC versus DC deserves some conversation here, and this is where we're going to talk a bit about the losses at I squared R, the current squared times the resistance that I mentioned earlier on, kind of makes another play. Historically, when electricity was first coming on, the AC and DC fought. DC was Edison's baby, and AC was Tesla, who worked for Westinghouse. And the first power grid, I think, was Edison's, and it was DC. And they fought over whether the grid should be AC or DC. And it got very acrimonious, and Edison, I don't know if it's true, but he claimed that AC was more dangerous and advocated electrocution as a death penalty option, and which he called being Westinghoused. It was that nasty. AC eventually won out because of the whole idea of three-phase power. So I haven't really talked about three-phase power. What I've shown is one coil of wire with one magnet spinning by it. But in three-phase power, you basically have three coils of wire. And you take power off of each one of them separately. And so you have three, you'll see commonly if you look at substations and the power lines going in, it's always in threes. It's because there are these three coils. You're generating power and as the magnet goes by, they're out of phase of one another by 120 degrees. So the advantage of that is if you think of those three coils, and now instead of a generator, you've got a motor. You can have a magnet in there that just spins. There's like virtually no moving parts. You just have one phase to this coil, one phase to the other coil, one phase to this coil, and you get a rotating magnetic field in there. This was absolute genius of Tesla's. And so you put a magnet in there, and the magnet will just spin. You don't need any extra wires to it. And that was a very efficient, very strong motor. And DC had other means of doing it. It wasn't as stable. The motors tended to be not as reliable or strong. The other advantage of AC is that you could change the voltage. Now, remember that the heating losses, the joule losses, the I squared R losses in a power line are proportional to the square of how much current is going through it. So you're losing power. The more current you send through a power line, the more the losses are, but it's not linear. It gets really bad really fast. So if you're going to send a lot of power down a line, to avoid those losses, you want, because power is voltage times current, you want the voltage as high as you can get it. So the current is as low as possible to avoid those losses. Right? Does that make sense? So if you're going a long distance, you definitely want a high voltage. With AC, it's very easy I didn't bring a demonstration of it. It's very easy to change the voltage. So if I have an AC, if I have a coil of wire like this, same coil of wire I had before for my demonstration, And I put AC power on across the leads here, so there's alternating current in this coil. Now remember, that's going to create a magnetic field, but because it's AC, the magnetic field is changing. If I put another coil of wire next to it, that's basically going to induce power in that second coil. And if I have twice as much wire on the second one, twice as many windings, as they say, on the second one, the voltage doubles. So it's exactly proportional to the number of windings, the ratio of the windings. So I can pretty easily change the voltage. I just need 2 coils of wire, and helps to have some iron in between them to funnel the magnetic field. So that's what a transformer is. Transformer changes the voltage, and the reason you want to change the voltage is you want a very high voltage on the power line. Now you can't have a really high voltage in the generator itself because remember, voltage is pressure, so it's how hard those electrons are trying to jump off that wire. So if you have 2 wires close together and a big pressure between them, the electrons will jump between the wires. That's not good. Things start to melt. So in order to have a manageable sized generator, the voltage can't be too terribly high. But if you need to send that power a long distance and you want to jump up the voltage, you could do that very cheaply with transformers with AC. The DC was more complicated and less efficient. And then at the other end, of course, you want to step the voltage back down so it's usable in people's houses. So take the voltage up, go a long distance over the transmission grid, step it down for neighborhood distribution, and then step it down further. The little transformer on the pole in front of your house, or behind your house in my case, to get the power into your house at 240 or 120. So that's why AC won out. But the reason I'm kind of bringing this up is because things are changing. It used to be very expensive to change voltage with DC, and it's much less so. And I didn't really realize this until I bought a little, what are they called? I don't want to say iPad. It wasn't. A Barnes & Noble Nook, a little device, a notepad device. And it came with, one of those charging things that you plug in the wall. Well, I don't know if you remember, they used to weigh about 1.5 pounds. They're about this big, and you plug it into the wall. Well, this one was this big, tiny. It didn't appear to weigh more than the weight of the plastic box it was in. In other words, it didn't seem to weigh anything. I plugged it into the wall, and it didn't warm up. What's in that box is a transformer. It's making 5 to 12 volts out of 120, and it's got a step-down transformer. It's all done basically with inverter technology now, because the cost and the efficiency of those devices has improved so much. The whole world of power electronics is changing, and you can now imagine a grid that is DC power. And then you don't have VARs, and you don't have frequency. It's a whole different world out there. And I heard an engineer from Intel saying, the world should be DC. And I thought he was crazy when he said it. It's looking less and less crazy.
Ken?
Yeah.
A question from one of the folks on the webinar. What was the motivation for development of the transformerless inverter?
The transformerless inverter, well, a transformer is a whole bunch of copper wire wrapped around a whole bunch of iron.
You're saying, for example, for solar?
For solar, well, so in general, although I started out by saying these transformers are cheap, they're certainly cheaper than the alternative for stepping up and down DC voltages, but it's a big hunk of iron and copper. So they're big, they're heavy, and they're expensive. So the fact that you could actually do an inverter without a transformer was huge. The things become cheaper and lighter, and probably now they're even more efficient.
Okay.
Yeah.
I'm sorry, I had a phone call, so I missed part of your thing, but my understanding is maybe engineers here can correct me if I'm wrong on this, but what I've been told by BPA engineers, the DC lines, like the big DC line that's part of the Untitled, Northwest Southwest Untitled, that DC line is much more efficient than the AC lines. But then the problem is it has to go all the way to its destination. Silmar, you can't send off. You can't have wires going off to San Francisco.
So I'm going to pretend that I knew you were out of the room.
Okay.
Which is why I didn't answer that question.
Oh.
DC more efficient than AC. So there's a big DC line from the Northwest all the way down to Southern California, and it's very high voltage. So first of all, the voltage is a big plus if you can get a high voltage. Now, a high voltage transformer, and even an AC, costs a lot more than a low voltage transformer. So you're not going to have a lot of interruptions in a high voltage line anyway. But DC is a bigger deal, because you have to convert the DC, first of all, AC to DC at a high voltage to get it on the line, and then DC to AC to get it off the line. That's all very expensive. So that's why it's for really long, historically, that's why it's been for really long distances. It's expensive to tap in between. So why is it more efficient? Well, it's more efficient because of the voltage, but the other thing is, okay, so this is part of the 10% why the water analogy, where the water analogy isn't there. Doesn't work totally. So the way radios work, the radio waves, is you take a piece of wire and you put alternating current on it at a very high frequency. And basically it's sending radio waves out into the world, and energy is associated with those waves coming off of that. So a long AC power line looks like a big antenna, and so we're just broadcasting that power to the ground and to adjacent structures. There's coronas that happen. So there's inefficiencies just because it's AC. And in fact, I mentioned earlier, I think the German railway system is at 13 hertz. They were one of the advantages of that is the efficiency gains from getting closer to DC, basically, not having the higher frequency, less radiation, less losses of that kind. Okay. Any other questions?
Not yet.
Okay.
One other comment.
So this would be a good time for other questions on this, because I'm going to kind of shift gears and start talking about high penetration renewable energy systems. So burning questions on what we've covered.
So this is probably ranks in the dumb question category, but your presentation so far has made me think of it. Can you contrast a little bit the net metering versus I realize that's metering, but your relation between that and what you've just done?
Well, there's a relationship at several points. So we talked about losses, heating losses over the transmission distribution system. So if you are creating power right at the load, you don't have those losses because you're not going over it. So what are those losses? Well, 8 to 10% on the margin during heavy load hours when, for example, solar is at its max, the marginal can be up to 20%. So the power, at the peak demand time at the house, 1 kilowatt hour there might be worth 1.2 kilowatt hours generated from a power plant. And then there's the whole question of reserves. If you net the load, you don't have to carry reserves on generators, the whole spinning, non-spinning reserves thing for the contingencies. You don't have those reserves either. So this sort of value of distributed energy comes into play in those two ways. Yeah.
Just real quick on that German train example. So what is the downside of having that lower number? Why wouldn't we, if it's more efficient, why don't all the systems go down to that? Is it more predictable load?
That's a good question. I think the downside would probably have to do with the size of the transformers, I think, or maybe the efficiency of the transformers. I'm not sure.
I mean, 60, as you said, is common for
North America.
North America, 13 is a big difference.
Yeah. Well, that's unusual. Most of the world is 50.
But even 50 and 13.
Yeah.
Anyway, it's
Yeah.
wonder why.
And the reason it came up was they were talking about doing an underwater grid for wave and offshore wind energy and doing that at a low frequency because of the long distances involved. Other questions? So why don't we take a 10-minute break and reconvene at 11:45.
Folks on the phone, you can dial back in if you choose or stay live. We'll be here.
All right, thanks. Yeah.
Question.
Yeah, this is actually like a nice time.
Okay.
I mean, you all probably are, but
No, he's our guy who.
yeah, I know. I think that would be very
Just wondering when you would like to address that.
Talk about let me write it down here.
Yeah, and you kind of learn why things live one way. Yeah, you
I might cover it. All right. I forget. You can.
I just looked up the German. It's just too complicated. And so they totally get that. Even that mentioned the earth. We need someone who's certainly
I have no,
practitioner called it getting gets it. I'm not sure that you're just having trying to stay up on it. Probably you'll take that, but they're going to lose after they do doing it. The illustrations of the electricity market, of course, is 80% different. And we're just, we're trying to be cutting edge.
What if it's for a little?
I looked up demonstration forces or current policy issues. That changes every time because it's whatever does. And so, last time, for example, we had all the players and things that were happening. So I don't know where that's going to go. My hope is they realize I was right. They'll get it.
I am full of
I can tell it's angry with me because a lot of
I'm glad you guys were able to make it.
trying to I said, look, I'm actually sure. How long did it take to help China get off coal? You don't pass up that option. And and I just tried to do both. The other thing is that I told you.
I'm wiring it home, right?
Yeah. I didn't have all my cylinders. You know, I was doing stuff, and I got everything. Eventually, but promise that she doesn't really seem to care that I answer or doesn't get it. Or I don't know. I've never had that conversation.
Transformers make it.
But from what I can tell,
Yeah, okay, right. I mean, I've got the 3 wires coming down.
Except as part of the equation. And so what happened is Western we're on
all 3, but only one of them is connected to your
really smart, brand new person. Because that takes it over in the future. So I'm doing separating the course into 2 sheets that were ready. Public power, private power, some field trips, pressure over in, we're going to have more energy mine stuff. Second half of the military, so they're going to do it to their story. So people can take control and reach me. That's what I was hoping to do at PSU, not going to let me.
In general, that happens to be that just the tax credit and stuff like that. That's the sense I have.
Someone. Or they drop it. Which is of course, where they have rocket hour. Our quick person is actually
right now we're kind of in
I'm giving the opportunity to advise the rest of them.
At first I wasn't sure if it was going to come. Now that I'm just going to handle it. I've been trying to, but we live in Selwood. Less than an hour, 55
You don't want to be too close to Dr. B. I've recommendation, it's not just someone like I basically
this might be too much work. It's cool stuff. It really is.
so that's where I am. Take me up on it. And then they can make their own. So that's the place to start. University and Northwest as well to help encourage them to develop it. They represent possibility.
And what's your about? What was your plan? I won't get into all that here. And so I think That's the sort of thing I want to start. That's very cool. I haven't really engaged to it yet, but I'm on the line. Yeah, I know, we're working on it. Well, you know, I get to, you know, the Ashland, and then that's exactly, yeah. That's what Lincoln does. Other spreadsheets
Hey, let's start thinking about getting started.
I'll go, Ron.
I want to launch into how you deal with really high levels of renewable energy. This is sort of the fun part. Have lots of questions. There are lots of pieces of this. Just to let you know kind of my strategy, most of the I'm going to go through kind of a laundry list of things that we've identified as steps to get from where we are today with our power systems to power systems can rely primarily or entirely on variable renewable energy sources. The laundry list is long, and you may some of them may stick out to you. Feel free to ask questions about those. I am probably not going to spend a huge amount of time on each of them. I will spend time on any that you want to talk about. I'm going to talk about this sort of identified fairly arbitrarily, I would have to say, 3 phases in the transformation. And I'm going to probably emphasize, at least my slides are going to emphasize the 3rd phase, which is not the most extensive, but it is probably economically and technologically the most challenging right now that we face. I shouldn't say right now, because that phase will come down sometime in the future. If we were to have to face it at this moment, it would be the most challenging. There are a lot of the challenges are institutional, and many of us in the room are actually veterans of some of those some of those institutional fights. First off, you know, it's possible. There's certainly there are island systems and isolated villages that are 100% renewable energy. The Northwest was 100% renewable energy. I tend to count hydro as a variable renewable energy resource. With storage, it has an enormous amount of flexibility. I know that later in my career, and we've talked about wind and solar, and sort of the idea of curtailing wind and solar was really troublesome for a lot of people. Coming from my hydro background, we did that all the time. It was a basic fact of hydro. I mean, we built huge storage reservoirs in Montana and Canada, and this huge DC power line and the AC lines down to California to make use of a variable resource that we couldn't otherwise use here, and we're just spilling. So I kind of facetiously talked about my background in hydro as being a 40% capacity factor resource, variable resource, but it's really pretty true. So there are islands at 100%. And Denmark, of course, is their target is 50% of their energy coming from wind. I think they're at 40 now. There have been days in Germany where all of the energy has come from renewable resources. And I know it's a big knock that, well, you know, Denmark has to export because they have more, you know, to get to 30%, you're going to have days where you're generating more than you can use, so they have to export it. And Germany, of course, Central Europe has got a lot of interconnections, transmission-wise, so the big knock is, well, they're relying on other power plants and other regions. But we did that with hydro. We export hydro all the time. If it weren't for the California market, our rates would be a lot higher. So it is a basic feature of variable renewable resources that interconnection matters, and finding a home for power that you don't otherwise have a home for is an interesting and an important feature of those systems, but it's manual. All right, integrating renewable energy. I think most of us are here for that. So there is a progression. These three phases I'm going to talk about in a moment. Today, basically, I'm on slide, good question. Why did that? 32? Sorry. The one that says integrating renewables with the chart, the green line on the chart. This is from Bonneville's system. The green line on the chart is almost a week's worth of wind data from Bonneville's system. And it goes from darn near zero to darn near, well, 4,500 megawatts. That's a pretty big number. There's a red line there, which is the thermal on Bonneville's system. And so today what happens, basically, it's no mystery that the wind goes away, the sun goes down. We planned for that when I was at Bonneville. Our big thing, when I started, our big thing was the critical water period. You would look back over the recorded history and find the biggest drought and how much energy could we produce over that big drought period. So sort of a minimum amount we could rely on. We called it firm. That's a big word. And we knew that when the loads were bigger than that, we'd have to have other resources to fill in. So we planned for that. And we're doing the same basic thing with renewables today. We know they're not always there. So we fill in with other resources when they're not. And some people have taken to calling that backing up the wind, which I find strange. We're really backing up the load, right? I mean, we don't care what the wind does. We care about meeting the load. When the nuclear plants came online, Rachel Shimshak loves to point this out, it was a big issue because remember we're talking about reserves. Well, reserves are often set by the single largest, what they call contingency, outage on your system. So all of a sudden the nuclear plant became the single largest problem. You could lose 1,100 megawatts in a few milliseconds. So you had to have other resources around to fill in for that. We call it reserves. Nobody talked about backing up nuclear plants. We're trying to meet load when the nuclear plant goes down. It's the same thing. So I know I fought with one utility who's in this room about that, but and I haven't won, but there it is. So there's what you do when the wind and the sun go away. It's variable and not completely predictable, and that's another challenge dealing with it. It's not really a new challenge. We had the demonstration here of what happens when you connect an additional light bulb to the system. The generators feel that. You can't predict when everybody's going to turn on their light bulbs. We have some forecast, obviously, of what the power usage for an hour or a day is. And then, the forecast is never exactly right. And then the load from moment to moment meanders around as people step into elevators and turn on hair dryers and whatever it is people do. They don't, it's not completely predictable. So that's fine. So there's some variability on the system, and we've had other resources around, controllable resources of various kinds to deal with that. So the wind on the system wasn't new, and it wasn't really a new problem. It was upsetting for a lot of, I would say it was upsetting for a lot of, real-time operators, because I worked next to them when I was at Pacificor. And, I was trapped in the bathroom with a guy who said, this wind energy is not worth anything. It's just not worth anything. I said, well, when the wind comes up and it generates a kilowatt hour, that kilowatt hour goes somewhere, and there's some other generator that didn't have to produce that, so there's, probably an opportunity cost savings there. And he said, well, yeah. He said, we only see the bad parts. Right? We don't really see the economics. And from their point of view, it's just bad because their lives, they face all this uncertainty. Power plants go offline. The load is different than we thought. I know at Pacificor, they made a big deal one year. The load was off by 50 megawatts on one day. It was different. Turned out the irrigators started a month early because it was an especially dry March. We didn't predict it. It wasn't in the forecast. So they have all this troublesome nature of the grid to begin with, and here you're coming with a generator. Now generators, normally they're friends until they break down because they're friendly because you have some control over them, right? So here's a resource you don't have any control over and adds to the uncertainty and variability of the system. It just makes their lives harder. And when I came on at Pacificor, I said, well, we already have to have some kind of reserve. It's not the same kind I was talking about before for when a power plant breaks down, but for the moment-to-moment, hour-to-hour variability, you have to have some kind of reserves, which some people call operating reserves, but other people use that term to mean contingency reserves. In the power business, we like to recycle words for different purposes, and it gets really complicated. But anyway, we have to deal with that uncertainty anyway. How do we do it for the loads? And I'll just apply that for the wind, because we're getting some wind on the system. And the answer was, well, we don't calculate that number. It's just whatever the operator feels like they need. So you get more experienced operators who are more comfortable operating closer to the edge than less experienced operators. There was no objective way of looking at the variability of load and during the ramp periods and non-ramp periods and calculating a number for the needed extra resources that have to be hanging around. So we kind of had to invent that, and the utilities have done that now. But that was part of this transformation. They didn't even quantify some of the reserve requirements that they needed to quantify. Yeah.
Is this still being done by as opposed to automated, as opposed to some in scenarios and programming?
Well, large parts of it are automated, but there are definitely people involved. Every day they decide which power plants they want to run tomorrow, given what they think their load is going to be and what the market prices are and what the gas fuel prices are. So they make people decisions, and then there are in the bigger utilities there are real-time operators who are watching the grid and making sure that things are going okay, and something always happens. And there are automated responses, but it's not all automated. So there are things that we could do with a little bit of wind. When the wind became more prevalent, then it makes economic sense to do things that are a little more outside our being utilities, normal operating procedures. And I would say we've barely tapped the ability of the power grid to manage the variability that the renewables are bringing. There's a lot of capability that we're not using, and we're starting to see some of the transformation, and I'm going to talk about it in a moment, with the expansion of EIM. So Puget is on, or nearly on, and Seattle is considering, and PGE is on, I think. Is that right?
Not yet.
Oh, not yet. Pacificor is on? Puget is on.
Arizona Public Service went on last Saturday. PG is going on a year now. Idaho Power in the spring of 18. And Seattle has agreed to go forward. I don't know if they have an exact date yet.
So this is very exciting, and we'll talk about why that's so exciting.
Yeah, we have to go back to council with the business case, but we're moving forward.
So I'm going to go through the laundry list in a bit, but something really changes at the higher level. I mean, going above 50 or 80, to get to beyond 50 to 80%, then you're looking at a world that's somewhat different, and it ends up getting more dominated by energy storage, and that is an interesting and large challenge. And I say that's a challenge if we were faced with that today, and I wish we were, but we're not. And I want to spend some time on that because I think that's well, the institutional challenges are formidable. That's the technological and economic one that I think we need to be focused on at some point and start focusing sooner rather than later.
Ken,
yeah.
Excuse me, but a question just came in. As you go into the next section about going forward, where we are right now, to what extent does hydro balance renewables today in the Northwest? Is there room to do?
Hydro does a lot of the heavy lifting. We are really blessed because we have more storage here in the Northwest than any other system in the U.S., certainly. So we have a lot of capability to balance the grid that other systems don't have. I remember when I was at Pacificor, we were listening to public service in New Mexico, and we were on a call, and they were talking about having to balance the wind on their system. What was their system? It was contracts and coal plants. And they were talking about all the things they had to do. We got off the phone, and my boss said, "What are we complaining about? They can do it." And really, the complaints, I think the complaints were out of proportion to the reality of it. So, yeah, hydro is a huge factor here, and it delays our need to do a lot of stuff beyond where other systems are. So the three-phase transformation, up to about 10 to 20% of the energy coming from variable renewable sources, by which I mean basically wind and solar. There can be others like wave energy. I've been involved in wave energy lately. But today, predominantly, we're talking about wind and solar. Up to about 10 or 20% of the demand being met by those resources, you don't have to do a huge amount. It looks like variable load. It makes that situation a little bit worse, and so you take additional action. I would argue, and we do argue in this paper, and by the way, on this slide 33 where I am, there's a picture of a report. That report is publicly available. You can Google it, get it, and it will go through this laundry list I'm going to show you in more detail than I'm probably going to go through it. And I do recommend it. It's readable, and it's fairly thorough. And we had, like I said, we had a large group of folks from around the world it's a great report to help us with it. Somewhere between 10 and 80%, it's going to become evident and economic that you need to do other things. For example, I'll just give a very simple example. Up to 10 to 20%. Like I was involved in this oversupply group at the council, and Bonneville literally made a federal case out of the wind curtailments. We weren't set up to curtail wind. I mean, it just wasn't something anyone wanted to do, obviously, and for good reason. But, at some point, it becomes economic to curtail wind over doing some other kinds of things. Now, there are lots of other kinds of things that you want to be doing, so that you do the wind curtailments as infrequently as possible. But, right now, sort of institutionally, we're set up to where that's not a thing. I mean, you really don't want to do that. Bonneville struggled and come up with a way of doing it that sort of people got calmed down about, but we need a robust system for doing that. And that came along as we had more resources. So you start needing to do some more significant work, and in fact this second phase has the largest number of things to do. Most of them are probably institutional. And then phase 3, which I'm more going to focus on in this conversation, unless people draw out some other things, is, how do you get really to 80 to 100% on a system? So, I showed that chart from the Bonneville system where the wind basically went away for a day or a couple of days at a time, and I've seen it go away for over a week, couple of weeks in the middle of winter. So if you're trying to be 100% renewable, you have to have an answer to that question. And that's, to me, that's the interesting challenge. Now, people tell me, we're not there, don't worry about that, but that's where my brain goes. And the good news is I think we have good answers. If we had to do that today, I think there are reasonable answers for how we would do it. Okay, so the 3 phases. Phase 1, so here comes the laundry list of things. I mentioned this first one, objective reserve requirements. Like I said, I went in, how do you decide how much reserves you need to meet the part of the load you can't perfectly forecast and the part that's just variable within the hour? So, well, we don't. You got to fix that. And PacifiCorp has fixed that, and I think most of the utilities with a lot of wind at this point have, because we're not at, I don't know, is any utility at 10%? The last I saw, we were around 6-ish, 6 or 7.
Out in the Northwest.
In the Northwest, yeah. Shorter operating schedule periods. So kind of by, nobody can tell me why, I guess by tradition, we have typically set up the system to operate over 1-hour periods. We call them schedules. So basically you have a plan for what's going to happen next hour. And you'll decide how much power you want from this power plant, that power plant, how much maybe you're going to buy in the market or sell to the market for the next hour. And then during that hour, as a utility, you're pretty much on your own, historically. And that's what this EIM is bringing, is you're no longer on your own. So in any event, that 1-hour period means, as a utility, if you're on your own, if you're not part of the EIM, et cetera, if you're on your own for that 1 hour, the variability within that 1 hour is much greater than it would be if it were 30 minutes or 15 minutes. So one of the things you can do is go from an hour schedule to a half-hour schedule. And it reduces the amount of extra resources you have to have hanging around just because, the loads might do something funnier than you thought they were going to do, and because they've had an hour to do them, it can be more extreme than if it's only a half-hour period. Yeah.
What's the pushback on the EIM? Like why are some folks, or why has there been hesitancy to join you?
So utilities like control. I think, well, for one, this is a hard question to answer, sort of, because everybody's got their different things. First of all, it wasn't originally EIM. It was an ISO. So an ISO is a big market where you have an overlord who's going to look out and take bids. You tell me what your power plant costs to operate. You tell me what your loads are. You give me a bid for your power plant, and we'll do the schedule, and we'll figure out the optimal set of resources to run, and then we'll tell you where to operate your power plant. Well, that's kind of extreme if you've been used to running your own utility and making your own decisions like that, and then you have to trust this guy, and who is this guy and where do they live and do they care about my power plants and my ratepayers and who are they to tell me what to do? And besides, in 2000, 2001, the ISO in California had this huge mess up where power prices went to, $10,000 a megawatt hour, 10,000 times the usual price, or 1,000 times the usual price. And then you'd say, well, what part of that do I want? And, justify that to your board or whoever it is. So that was the original presentation, and then it was, well, we looked at doing things that are short of that, and the EIM is one of those things that's short of that. So there was less resistance to the EIM. You have some of the same issue because you're giving control over to somebody else. You have to give them your loads, and utilities are sort of, in my view, notoriously secretive about everything about their operations. They don't like to let it out of the bag. But that's just my view. I don't know. Do other people have different views of that?
Well, I'll just add one very quick addition. It's a slippery slope argument that, a energy balance market could potentially lead to an ISO, especially because so there's concerns about California ISO and how they will be the dog and we're going to be the tail. And then there's the traditional concerns that public power utilities in the Northwest especially have about giving up control to, they think they could have more influence over BPA than they would have over an ISO.
BPA has governance issues as a federal agency, and I know a lot of the enviros have been concerned, especially Sierra Club. Coal plants typically, or historically anyway, have had very low cost power, and they're concerned that that expanding the market with the EIM and more especially the ISO, which is basically just the EIM on a different time scale, gives more market access to the coal plants.
Do we know what the operating schedule is for the California ISO?
The operating schedule?
1 hour.
They have a day-ahead market, they have a real-time market, and they schedule and operate basically every 5 minutes.
Yeah.
It's more complicated than that,
they're sort of based on an hourly schedule, but they have a 15-minute market and a 5-minute dispatch, so they've gotten much closer. So just to kind of go through my little laundry list here. So shorter operating schedules. So Bonneville did this. We argued it in the rate case and originally in 2010, and they said no, and then they did it. I'm so happy, so that you could schedule your wind project over a 30-minute or even a 15-minute period, which took a lot of the burden off of Bonneville, frankly, and put it on the people receiving the power. So less reserves were needed. Shorter gate closure times, so you have to nominate what your generation is going to be for the next hour, or now 30 or 15 minutes, preferably, but historically it's been an hour. And you have to do that at some period prior to the beginning of that hour. Well, how long a period? Sometimes it's 90 minutes, 120 minutes. So basically, if you're trying to project what your wind project is going to produce 2 hours from now, it's going to be a lot less accurate than if you can project it for just 30 minutes from now. And that's that gate closure time. So shortening that is a big help for wind projects. I think in phase one, if you're looking forward to this full transformation, or at least getting to phase two, you have to start doing demand management. Because there's a lot of flexibility in demand that historically we haven't tapped. And, if you're, before you get to 10 to 20%, you need to at least start doing demonstration programs to show that and find the low-cost opportunities. Expand the sources of ancillary services. This is a little bit arcane, but remember I was talking about the variability within the hour, and you need power plants you can adjust up and down, and absent the IM, you're kind of on your own within that hour. And so if you're Bonneville, so I don't mean to pick on Bonneville because the other utilities would suffice. If you're Bonneville, for example, historically, all of that balancing has come from the hydro system. Well, it doesn't have to. You could have a market and take bids for balancing services from other power plants that are interconnected to Bonneville, or even the wind projects could promise to reduce or limit their output if you gave them a shot. But historically, each system, and we have 16 or so in the West here, has the way it's set up under FERC. The transmission provider provides these balancing and other ancillary services for the system. So if you connect them, if you're a load, you get charged by the transmission system. They don't have any resources, so historically they would go to their generation side to get those services. So PG would go to PG power plants. Bonneville went to Bonneville power plants for all those services. They don't have to. There are other resources in the region, and another thing we argued in a Bonneville rate case was, look, there might be cheaper sources. The hydro system is great and it's cheap, but not always. And they were trying to provide a high level of ancillary services even during droughts, even during flooding, and it's not always available. So what they had was sort of limited, so we urged them to open the market. So that's another thing.
And there are other uses of the river, important uses of the river.
No. No, they have certain limitations that they have to live within, and the point being that there's other power plants in the world, but historically the transmission providers in a utility only went to their utility suppliers. So we need to open that up. And review grid codes. I remember early on, this is another arcane thing, but it harkens to what we were talking about, inertia. You can get inertia from inverters, but you have to require it or ask for it. Ireland has a requirement like that in their grid code for wind projects.
Could you explain grid code, because that's not a term that's used very much yet in the U.S.?
What should I use?
Well,
is there a different term that's more?
Standards, I don't know.
Standards, okay. So standards for the inverters, for example, to require them to have certain attributes, like to provide inertia. I remember early on at Pacificor, we had a bunch of wind in Washington, southeastern Washington, and the standard for the devices, for the wind turbines, was that if the voltage went to zero, which it does, like if a tree falls onto the power line, it gets grounded, and so the power goes away. If the power goes away, then the wind project was required to turn itself off. So, but what commonly happens on the transmission side is you'll have a limb hit a power line and it explodes or burns up and the problem goes away. They have circuit breakers that open up, interrupt the power, and then they wait a little bit and they try to reclose. And they do that 2 or 3 times before they decide to give up and just leave the power off. Well, the wind projects were always just going off, and that was because they had that requirement. Well, there are a lot of these requirements, like the solar issue that I talked about, that you need to take a look at that don't necessarily make sense for renewables. Phase 2, we're going up from 10 to 20% to the 50% range. You really need to start expanding markets for flexibility, not just thinking about it. And that's partly what the CIM does, and the expansion of the ISO. It's where, Puget's not on its own during the hour, and PG's not on its own. It may be that, my loads are higher than I projected in my little utility on a particular moment when the utility sitting next to me, which I'm electrically interconnected to, has 2 lower loads than they expected. And if we just average the 2, neither of us would have to do anything. We wouldn't have to do as much anyway. So sharing that kind of thing, and sharing that so that all of the sources of flexibility are allowed to come into the market and supply flexibility. Because right now, like I said, historically the transmission provider has gone to its power compatriot. Reflecting wholesale market prices at the retail level. I mean, there are a lot of utilities, you were just saying about Seattle being long, a lot of utilities are long. There's some great energy conservation coming down the pike with these carbon dioxide heat pumps, the LED lighting, we have rooftop solar, so loads are dropping, and you're going to get these times when there's this, trying to call it overabundance, this abundance of renewable energy. What do you do with it? Well, let's let the market decide what to do with it by when the price goes down below, $10 a megawatt hour or below zero, then you make that temporarily available to loads that can make use of it. And I suspect we will see a lot of creative uses for that power come up, which will probably involve energy storage in one form or another. So we're going to need to do that, and the utilities are going to need to expand their markets too, so that we're starting to provide transportation and maybe even more industrial loads. I understand inductive heating is a potential replacement for some of the fossil use.
So you're talking about dynamic pricing at the retail level?
To some extent, yes. Remove penalties that are restricting renewable resources, VRES, variable renewable energy sources, from participating in the market. So there may be contractual limitations. There's a production tax credit. There are limitations to their ability to participate, and there may be, performance penalties. I know when we wrote our contracts at PacifiCorp, if you didn't generate, when you could have generated, then you were penalized. I actually wrote into the contracts I was involved with that we would pay them as though they were generating, and we had the option of turning them off anyway. Allow negative wholesale prices, and the public in the room may hit me, but you're not going to get market solutions for energy storage and flexible demand if you're not reflecting the negative wholesale pricing, and it's not just due to the production tax credit, I might add. It takes a while for a coal plant to come back online. And I know I talked to some coworkers at PacifiCorp when there was some negative pricing, and they left their coal plants on. And well, why did you do that? I said, well, we were making enough money on the coal plants during the day that the negative prices at night weren't enough to induce us to take them offline. So in other words, they needed more negative prices to knock that coal plant offline. So the coal plant startup and shutdown costs, this is not just a renewables issue, this negative wholesale prices, and it's not market manipulation. I mean, it could be at times. I'm not saying it never is. But there are real good economic reasons for negative wholesale prices, and I disagree with...
Today.
They what?
I mean, their prices are negative in the mid-C market today.
Yeah.
And in California, one is down to $249, I believe, or $150 or something, so negative.
Yeah, and it's just going to become more and more prevalent. What to do about it? Let's find some loads that can use that energy. Okay. Peak demand contribution. There's been a lot of progress on that. There were people advocating for a long time that wind doesn't contribute to meeting peak demand. I think statistically that's not true, and it's demonstrable, and you need an objective way of calculating that, and certainly for solar, which has a much higher fraction probably than wind does, depending on the wind resource. The production incentives to encourage diverse deployment of resources. So this is about, if you site all the wind in one place, then it's highly correlated and they all go off sort of at the same time. And so there's some value to diversifying their location, even across time zones, potentially, for solar, certainly. So looking at that, implement. Oh, and these baseload plants, I know utilities love them, but they're really an impediment in many cases because you can't turn them off. Like I said, you need higher negative prices in order to turn them off. And if we need flexibility in the system, they're not flexible. Or to the extent that they're not flexible, you need to start thinking about getting rid of them to get to high levels.
Some examples of policies that would do that.
Carbon policy. I'm not a real policy guy.
Well, in the East, in the organized markets like PJM, the older, less efficient coal and even some gas plants are basically being retired, and now some nuclear plants, because they don't offer the flexibility, they could withstand a little bit of negative pricing, for example, or whatever, but not a lot. And so the most inefficient ones, the oldest ones typically, are the ones that are basically being, the economics is just there now.
Yeah, the market may sort a lot of that out. If you're trying to run a baseload project in an environment where there are a lot of negative prices, you're going to soon find that it's not that economic.
They're already being perceived as stranded assets, and that will continue as flexibility becomes.
One of the things that's happening is that in my home state of West Virginia, which is one of the few still regulated markets, the subsidiaries of large power corporations are trying to basically dump their coal plants on West Virginia for exactly that reason. One place they can be assured of some return anymore.
Hey, can I ask a question? So, I'm wondering if you have thoughts on, because in the integrated resources plan, it all comes down to cost. And one thing that I think we're seeing is that the cost of either existing baseload or even new CTs is still coming out lower, although it's closer, but still lower in the analyses that the utilities are doing than, more flexible, even more flexible natural gas units than a CT, or, let alone renewables. And I'm wondering if there are things we should be looking at in terms of that cost analysis that we should be examining more closely to see if there are inputs that are, wrong or a little off in the analysis.
Yeah.
Push on.
Yeah, we can talk about that, I think, separately. I think I saw some of that going on in one of the IRPs, but yeah.
Can I just ask that people not use initials, so a CT is
a combined cycle.
Or combustion turbine. It's a jet engine to make power from natural gas.
Thank you.
It's a type of natural gas.
And the IRP is the integrated resource plan the utilities do to determine what kinds of power plants to add. All right, I'm going to soldier on here for a bit. Implement system-based energy storage valuation methods. Valuing storage turns out to be kind of difficult and complicated, and it'd be nice to start focusing on that, and I see Portland General Electric is doing some of that, and some of the other utilities. That's a good thing. So phase 3, so this is the one I want to focus on a little bit more. What do you do beyond there? So the earlier conversation was to deal with some of the variability and uncertainty that we have, and I guess there was a question on timescales. It happens on all kinds of different timescales. From you saw that one chart that I gave from Bonneville with the green line for wind, where there was variability over days. So there's that kind of thing, where the wind was sort of there, and it was sort of not there. Then there was the kind of the in-between times when the wind was ramping up or ramping down. And that happens over typically a minimum of, I would say, 2 or 3 hours up to 12 to 16 hours, where these big, large-scale weather systems come across the region. And then there's the variability from hour to hour and then within hours. So there's flexibility on all these timescales that turns out to be interesting and important. And I think the phase 3 is really about the longest timescales, when the wind goes away for days or weeks or even months is possible. So what do you do then? you need to make sure that you still have what we're doing today, that when the wind goes away, you have enough resources of some kind. The resources may be generators, they may be storage, they might be demand side, some combination of resources. So, this is obvious. We're not just going to turn the lights out when the wind goes away. So you got to have that. You need to, at this point, phase out. At this point, you can't have any baseload fossil resources or nuclear if you're, set on doing totally renewable resources. Those have to be out. I mean, by this time, those are out.
You call them inflexible because they have to have a certain, they have to be operating at all times to be able to fire up, or?
That they take a long time to turn on or turn off. It turns out you can actually design coal plants to be flexible. But if we're getting to 50 to 100%, we're not going to have a lot of coal plants hanging around. And certainly at 100%, there's not going to be any. And you can retrofit units to make them more flexible. It tends to be expensive. But the older units probably at this point aren't going to be economic. They'll probably be gone. I think at this point you have to have policies that allow the optional use of electric power. And the one that leaps to my mind, because I don't know, it's just me, I guess. But when the wind comes up, the first thing you do is you turn off the most inefficient gas plants because they're the most expensive ones. So you turn off the most expensive stuff first. I mean, just economically, that's what happens. So you turn off the single cycle, the least efficient combustion turbines, and then you go after the combined cycle units. Eventually you get to coal, although that might be changing. Maybe coal is first or higher in the list. At some point it gets displaced. And then you're exporting power, and then eventually you're curtailing energy. But it seems to me if once we've displaced the gas power plants, why aren't we displacing gas water heaters, other uses of natural gas? So for example, an electric water heater is a very inexpensive device. There are no moving parts. You could have a little electric water heater sitting between your cold water supply and your gas water heater, and it just sits there until the wind comes up in the middle of the night and the prices go down to zero. You start heating that thing. Or you start preferentially heating your hot water with electricity either in the middle of the day if you're a solar utility, or in the middle of the night if that's when the wind is coming up. But you need to develop policies that allow the market to come in and do something with those opportunities. Maximize use of the transmission grid infrastructure, getting out to other power systems so you can share the variability and share the resources that you have, and distributed generation, like I said, that reduces the losses, so there's less need. Energy efficiency has a big role to play, because if you're going to get to a high level, energy efficiency is a least cost option usually. And then end-use flexibility options, things like water heaters, but HVAC systems. Eugene Water and Electric Board has a great project. There's a gravel pit, and they have to. It's next to the Willamette River, and it fills up with water, and they have to pump the water out. Well, they can do it at random times, or when their retail rate is lowest. Or basically, it looks like a pumped hydro project. They can use that flexibility to help the system out. And it's those kinds of things that you're going to want to maximize. The variable renewable energy resources are going to have to be providing some amount of the ancillary services, maybe a good amount of it, through these new standards, which I was calling grid codes. So here's my more focused look at the sort of the phase 3, which necessarily ends up being about energy storage at some point, because you're trying to bridge days and weeks and maybe even months where the renewables aren't there. So the only option then is somewhere you've stored that energy and you're going to recall it. Now, everybody's leaping to batteries because, well, they're sort of understandable and their prices are coming down tremendously. But using a battery to bridge weeks and months is economically infeasible at this point. It's just sort of beyond the pale and may well be into the future. And what I'd like people to think about is a more general view of what energy storage is. So I'm slide 38 here, generalized view of energy storage. I'm representing the grid by this red block in here with the transmission tower. It's supposed to look like a transmission tower. And we normally are thinking of energy storage in terms of electric power coming out of the grid going into some device. Maybe it's pumped hydro, compressed air, batteries, some sort of storage device, and where it sits for a while in some form, not electricity typically, and then gets called back as electricity. Okay? That's really only one of three mechanisms, and I think if we concentrate on that one, we're sort of missing the boat on a lot. And this isn't really all that far out there, so some of these things will be familiar. So my chart here has primary energy fuel basically coming in to the power plants, which feed the grid, and then end-use devices like your refrigerator or motors or whatever that take the power out of the grid and use it for some purpose. And there's really energy storage opportunities. There are energy storage opportunities at each leg of this. So a very simple example, obvious to those of us in the Northwest, is the water stream flows, the ice melts, comes into the hydro reservoirs where it's stored until it's needed. So that's this cylinder on the left, lower left here, represents things like hydro reservoirs. So that's a very obvious thing, but it's not the only one. So for example, we have a natural gas system that's really quite huge, and there are natural gas wells that feed energy into that system, and we take it out to run the power plant more during the day, for example, than at night. And in between times, that energy is sitting there stored in the ground and in the pipeline. Coal piles are another example, diesel fuel tanks. All these things are primary energy storage capability. And if we could somehow leverage more of that, that's as good as this other kind of middle. And then at the end, we have storage capability on the end user side. So for example, I always cite, I have this tattooed on my head, I guess, electric storage water heaters. Great example. When you turn the tap on, the water that comes out is heated, maybe 10 hours ago. Nevertheless, your water heater just came on. Once the tap's open for about 30 seconds, at least mine, the water heater comes on about the time you're using hot water. It doesn't have to. The water you're using was heated a long time ago. So we actually use that energy storage. The water heater has about 6 kilowatt hours. And of course, well, the biggest demand response program in the Northwest is in Idaho Power's irrigation. So you can irrigate all the time, or, well, gee, there's a lot of storage in the soil. So you can irrigate preferentially at night or just interrupt it during the day, and that's using it. And insulated buildings. Any insulated building basically is an energy storage device, and right now the thermostat is set at some number, say it's 70 degrees, and the actual temperature in the room is constantly going up and down around that 70 degrees, and it hits a lower setting, the air conditioner, or an upper setting, the air conditioner comes on to cool it down. Well, all that happens at random. It doesn't have to. It doesn't have to pre-cool the buildings, or even within that little narrow window that the temperature sits normally, we can coordinate. It doesn't have to be all at random. These are significant energy storage opportunities. And here is, to give you an idea of the order of magnitude of things. You know, this chart is very deceptive, and I've had long conversations with people about it. It is not a linear chart. It's a logarithmic scale. Something is if one block is twice as big as the other, it's in real life it's 10 times as big. But in order to get everything compressed onto one chart, I had to scrunch it down in this logarithmic chart. So here's my standard candle. This is the energy storage of Grand Coulee Dam, the reservoir behind Grand Coulee Dam, FDR Reservoir. So as I said, water heaters contain about 6 kilowatt hours of energy storage. There's about 4 million of them in the Northwest. That's, you know, smaller than Grand Coulee, but it's big. We talked, there were proposals for a large 1,000 megawatt pump storage project in the Northwest, cost $2 billion. You know, that's that big. So the water heaters are significant.
How much would the water heaters cost?
More than that. About a tenth, I think. So that's a regional side of the graph, and then I have on the national side, the national natural gas system is this big, so it's not quite, it's several hundred times as big as in the natural gas system. Remember that, because I'm going to come back to it. And then here's, if we had 150 million electric vehicles, which of course we don't have, that's the energy storage capability of that. I don't have the 50 million water heaters that are in the U.S., but that would be significant, but not as big, obviously. Yeah.
When you talk about the electric vehicle storage, are you assuming that we've got sort of a standardized technology to full electric vehicle battery power?
Yeah, you know, not all that would be available at one time. Yep. Yeah, there are a lot of it. I'm just trying to give you an order of magnitude notion. And the point being, the main point being, the natural gas energy storage system is huge.
Sure. Well, I mean, Drive Oregon had a presentation last week where they're showing these home to leaf or leaf to home inverters that would pull, that are deployed in Japan right now, that pull the energy, you know, 3 days worth of energy out of a car.
Wow. So demand management, this is actually, the picture on the left is a photo I took in Copenhagen. These are insulated water tanks, hot water tanks. They have district heating systems in Denmark. 60% of their buildings are in district heating systems, and they have these huge insulated hot water tanks that's sitting next to a coal plant which is generating electricity. The electricity isn't generated in the same shape as the hot water usage, so they have these big insulated tanks. And what they were saying was that when they got to high enough levels of wind penetration, they're going to put electric resistant elements in there so that they can dump the heat in there and use it at any time virtually in the next couple of days anyway for heating homes. And this is another power plant in Denmark that can have, with another insulated tank, they can produce energy, they can consume energy, and they can store energy.
And I understand, Ken, that Denmark is moving in that direction with the wind. So, yeah, with their storage tanks.
Cool. Yeah.
Do they have a pipeline from the tank to people's homes?
Yeah, yeah. A huge investment, which I'm not saying we would do.
Heating, so it'll be, you know, a chunk of Copenhagen.
Yes. They chose to distribute their power plants throughout the country instead of a few large power plants, so that they could do these district heating systems.
Ken,
yeah.
Question. Could you speak to the potential for storage available by variable operation of the hydro system downstream from Grand
Coulee? The available storage capability is used, basically. I think John Day probably has the most storage, and then the Dows. but Grand Coulee can store for months. And John Day, I think, for days over a weekly cycle, and the Dalles is maybe hourly. So much reduced storage capability downstream, but the flexibility there is all leveraged by the Grand Coulee releases. So.
One other question.
But you can also turn on or off individual turbines or throttle turbines.
What is the overall storage capability of a water heater, gigawatt hours?
So an individual water heater stores about 6 kilowatt hours of heat at 120 degrees. We did a demonstration project with Bonneville where we used 100-gallon tanks, operated 160 degrees. We were able to get 20 kilowatt hours of energy storage in there. It was about the equivalent of a Nissan Leaf car. And we could store about 3 days worth of hot water for the household, which means that you could dump that energy in there anytime within about a 3-day period. It's a huge amount of flexibility, not months, but hours and even days. So I want to circle back here to gas. We are running into the end, which is a good thing. So I want to talk about gas for a minute. The role of gas in gas power plants. I think that gas will have an increasingly important role to play. I know this isn't politically correct, but bear with me because it has a great ending. So right now we're using gas resources, like these combustion turbines, and there are others, reciprocating engines, which are basically big diesel engines, but they usually burn natural gas, have a lot of flexibility, so they're in favor right now. They're relatively efficient to where they used to be. They're not the most efficient way to use gas, so there's that, and that's important. They're a great complement to wind and solar. In other words, you operate the gas plants when the wind and solar aren't there. They don't do everything. They don't do everything. You know, we talked about, we have to have these gas. Bonneville used to do this. We have to have gas plants at some point to integrate the wind. Well, when the wind is at maximum output and supplying most or all of the power requirement, all of your gas plants are turned off, so they're not integrating anything at that moment. So they're better for when the wind is at lower levels and you need to vary the complementary generation up and down. And they fill in so that big gap that I was showing. But what I want to talk about is for gas long term in terms of energy storage is that they can burn more than just natural gas. For example, they can burn hydrogen, they can burn ammonia, neither of which has carbon in it, and we actually have an example of a power plant, or a plant, not a power plant, a plant that's producing methane, which is the primary component of natural gas. This plant produces methane from the effluent of a biomass plant. So the biomass, this is an actual plant in Germany. The Audi car company built it. It's been operating since 2013, 6 megawatt plant. They take water in, they take basically the smoke from a biomass plant across the street. They pull the carbon out of that gas, out of that smoke, and they recombine it with hydrogen to make methane. So if you believe the biomass is carbon neutral, then this methane is carbon neutral. And in fact, it wouldn't have to even come from burning anything. You could pull the carbon dioxide right out of the air. It's not cheap, but now we have the bridge fuel that's carbon neutral. It's a huge battery, basically leveraging the natural gas system, which I showed you has a huge storage capability. But these gas power plants burning carbon neutral fuels instead of natural gas. And I think ultimately we're going to start having to have carbon standards for the natural gas system, for the gas system. Synthesized, unnatural gas, carbon neutral gas that we'll be burning. And some of it may be hydrogen. Yeah.
So we had some folks from Canada visit us They have a really interesting technology that basically uses the PEM to take the hydrogen out of water, and they're injecting it back into the pipeline and selling it to the gas company as renewable natural gas. And I guess in Europe, the standards for the amount of hydrogen you can put in the pipeline are a lot higher than they are here now. But they actually have a university in the Midwest that is doing this, and they're supplying oxygen to the local hospital too.
Yeah.
But it just occurs to me that you could literally have a gas plant there also, burn that hydrogen.
That's right. I called my former colleagues at PacifiCorp when the Oregon storage thing came out, and I said, I hope you look at this, because you could produce hydrogen, inject it into the gas system, up to, the number is different depending on the system, but between 5 and 10%.
They said 15 to 20 in Europe.
Yeah, probably so. Up to 10%, I've seen you don't have to change the burner tips. It just burns. Hydrogen has less heat per unit of volume, but you can inject some percentage into the natural gas system, and that's where we'd start, because producing the hydrogen would be a lot cheaper than producing the synthetic methane. But that's, I think, where we're going, and that's where the storage is. So this big battery is the gas storage system and pipeline system. Part of it is, that's where the storage is, and then the part where you get the power out is all the power plants we've already built. And the only extra infrastructure we have to build, instead of these phenomenally expensive batteries that would be economically prohibitive, is you'd be generating a combination of synthetic methane and hydrogen at a low level, putting it into the existing infrastructure to burn in existing infrastructure and be carbon neutral. And that power would, kind of leak. You wouldn't need, hundreds of thousands of gigawatts of this, because 80% of the time you're probably getting the power directly from the renewables. It's that 20 or 30% of the time when they go away to such an extent you have to burn something, then that's not a huge amount of energy, and that's where I think it would come from. So that's kind of, at least barring, huge technological breakthroughs, if we had to do it today, that's, I think, what we'd be doing. And it's not that expensive. So that's pretty much my talk. This is a summary of what I just said. So, I think we need to do demand management. We need to do all the energy efficiency we can. We need to expand our markets. Again, expanding the markets lets us average the variability over larger areas so that there's less of it in total. The total is less than the sum of the parts. And we need to go out and grab the power plants that are out there so that everybody who can participate does participate in the most economic way, and that's what the energy imbalance market, the EIM, and the independent system operator, the ISO markets, that's what they do. I would say don't shy away so much from limiting renewables. I think that's our future. It is probably one of the last things we want to do. We want to do this market expansion and the other things first. You want to be able to reflect these low wholesale prices down to entrepreneurs at the retail level that can do something with it. And ultimately, we're going to need low carbon standards for the gas system. Yeah.
I know we're running close to time, and I certainly agree with you about the residential water heaters. I'm wondering if you can talk a little bit about the potential for industrial customer partners.
Well, the industrial demand management is much cheaper.
Yeah.
Because they're bigger, they're in one place. With the residential, you have to go out to everybody's house, and each one's only 4.5 kilowatts, and it's expensive. So the industrial stuff is good. What's nice about the smaller ones is that you can do the same thing in each one. It's very replicable. But typically the industrial programs are cheaper, and it's the lowest hanging fruit. And commercial HVAC is huge. Ice storage systems, Bear device. There's a huge amount of progress. And I mentioned the carbon dioxide heat pumps. Northwest Energy Efficiency Alliance has done a field test of 5 of them. They just got UL certification. They're 50% more efficient than today's heat pump technology. You can use them to heat your house, even if you burn natural gas to make the electricity and send it to the house to make the heat. It's more efficient than burning the gas directly in the house. They're that efficient. This will be a whole new world. We need to get the consumption down. That puts pressure on the utilities. We need to expand their markets into industrial and transportation sectors at the same time. That's how I think. And you can read the report. Thank you. And if you want to call or email me, my information is up here.
And is that island, oh, sorry, you want to...
Oh, no, go ahead, please.
Is that island just, close to 100% wind, that's being done for storage, or what are the...
I don't remember. I did that a while back. It might have some higher. Costa Rica is close to 100%, but they're like 50% hydro. I don't think the island had hydro. Yeah. I think the island had hydro.
Yeah, so to simplify your storage thing, being the most balanced with the environment would be we would use natural gas sort of plant to generate when the solar or wind were down, but we wouldn't use natural gas necessarily, we'd use hydrogen.
Yeah.
And then the oxygen we could sell off to wherever else. Is anybody doing that?
Oh yeah, I was talking about people certain.
Hey everybody, thank you all so much for coming. Again, we've got on the 24th paper performance, so hope to see you in Olympia.
That part's the easy part. Yeah, they're doing the technology upgrade. Their whole market, and yeah, I mean, we need to take a look at a few other things, Fred, wear and tear on our power plants, a lot of internal swirls. Yeah, we're hiring consultants, done
but you nonetheless.
I feel like all right, something very what do you think?
Yeah. I know. The thing is something coming around to these thank you for being get a story.
They talked about doing
Robert, he's
Hey, Dick, so we got our solar education manual done.
Yeah, Sean had already been in contact with our people.
That's one of the tough things right now, the way the products are priced.